Hello guys, we're from Theodore Studio. This is Paul, Flavia, Dmytro, and Aris. So we start from our design status. So basically what you just saw is like a building life cycle in the current status of the production of our building environment, which is very energy consuming, time consuming progress. And it's defined by its finite use of labor and materials. So our design proposal, we call it noMad. It's kind of behavior-driven fabrication system. We mark the shift from architecture as finite, and instead we use autonomous, non-finite, real-time solutions to adapt dynamically to the demands of its environmentally solutions. So the key properties of our systems, the first one we call is non-finite, which means when after the usage, the units of the structure can go somewhere to find another site and rebuild again. And thus, these sites remain static until the whole structure demolishment. And another one we call is mobile. Mobility is very important for our system because it makes the transformation of the single unit by its locomotion. And the third one we call it the self-assembling system. The self-assembling inherent in the unit's body with no external like human intervention or the mechanic intervention. Another one, the first one is called self-structuring. So this means, because you can see the polyhedral structure, there is no external necessary to use like trusses, scaffolding, or other support materials. And the fifth one, we call it self-awareness. The self-awareness of each building block, meaning enabling architecture with a sensory system, which means a single unit can sense its single current statement, and also it can sense the surrounding state of the other units and then make a decision what it's going to do in the next step. And then finally, we call it localized deciding. So our fabrication approach of the negotiated space is neither bottom-up or the top-down strategy. We use goal-orientated with localized decision making by unit-to-unit communication instead of deterministic superimposed building plan. So the second stage, we start our initial research. By the polyhedra and the transformation, the first thing we get inspired is by the person who called Alexander Graham Bell, who invented this this kind of cars. He was the first one who invented the space frame and also the telephone. Everyone knows that. So, like talking about the cars, which he get inspired, like say the cars can have different flying behaviors. So we kind of want to play the polyhedra to say what kind of behaviors of our, like say the physical model over there. So I will start playing with that. And then we kind of go to Buckminster Fuller's theory of it's called synthetic, sorry. Yes. So here, our initial research and form finding was grounded in specific polyhedra, their packing and decomposition logics and kinetic qualities. We explore how a geometry can transform and what are the implications on its connected surroundings.
So the system that we propose, according to our research, operates on 3 different scales. There are 3 scales of autonomous intelligence. Each scale can autonomously self-assembly to the next higher order or to the next higher scale of organization. 3 scales that our system operates in is the single unit, the smallest determinator of our system, which has some simple abilities of transformation and self-awareness, enabling the next scale, the medium scale, where kind of the collective intelligence of our system starts. The medium scale is a shape runner of simple body plans with mostly high mobile qualities or high transformational qualities. And from the medium scale, our system self-assembles to the large, high population of the scale, which mainly has spatial configurations and spatial qualities, acting as a collective and a collective behavior where the parts of the system interlock and therefore lose its mobile characteristics, but instead use the transformation for optimization and adaptation through reconfiguration of the system. So our main unit, our building block, is based on a simple rotational movement of the faces of an regular octahedron around the vertices of its neighboring faces. And within this transformation, our unit starts from octahedral state, expands to an icosahedron, cube octahedron, and contracts back to another icosahedron and octahedron. And within this transformation, the unit expands up to twice in its size and changes literally all orientation and location of its faces within the unit. So when we analyze this unit and its characteristics in detail, we see a series of different relational changes within one unit of directly opposing faces that only make a linear translating movements, or diagonal faces that relocate and rotate towards each other. So this breaking of the grid, how we call it, drastically changes the unit's potential to the search space of a single unit, meaning the possibilities of aggregating to another units and allowing new connections. So you see in the bottom right how, according to the transformation, not only the single unit changes, but the whole, through a local transformation, basically the whole entire global system gets relocated and reconfigured and can expand or move to different areas.
So our main unit has different, several abilities, design abilities embedded in it that can enable it to act autonomously. One of them is the activation of the unit, is this translation from octahedron to icosahedron, and this translation that can break the grid and trigger different organization in the space. We also have soft faces. These soft faces can allow the unit to autonomously connect and disconnect to the whole aggregation, and it can also work as a constraint when these faces increases to the inside, not allowing connections when they are not necessary or not desired, like in an overload aggregation or something. So yeah, these faces, it can trigger the ability of the single unit to communicate to its neighbors and find possible connection systems. We also developed different prototypes to explore these movement abilities of a single unit. So we activated the faces to make the single unit move. Also, we worked with these soft faces that can pop in and out to enable these connections with the neighborings. Also, we have these central connections that it gives kind of freedom to the connection of the units, because they can rotate around the axis, or the corner connections that is more structural, for more structural purposes, like in this one, as we can see. This is a model where we call a walker. We're going to talk about it next. So we developed an ecology of machines that are mobile bodies with creature-like characteristics and very specific behaviors. These creatures are the first level of intelligence in our system because they can act collectively and autonomously. These bodies are made out of active units, as we call, and passive ones. And by the activation of these active units, the passives are triggered in the movement. So the behavior of these machines are directly connected to its body plan configuration, as well to the sequence of activation, or the choreography, as we call. Because depending on the way it choreographs the movements, it can behave like a snake, or it can walk like a legged body, or it can have movable and translating arms. And only a few units are active, so we kind of we don't have we decrease the amount of energy inputted in the system by having only few actives, activating a lot of units. So in this image, we can see how these units, when combined together, there's different connections, opposing faces or diagonal faces. They can trigger different movements. So in this case, we have the diagonal ones that creates rotating arms, or the opposing faces that acts like lifters of matter or something. And when this taxonomy that we created can be read as a genetic sequence or a shape grammar, where we have simple body plans and simple choreographies that, when they come together, they trigger a range of movements to our system. In order to simulate a more automated and goal-oriented movement sequences and communication, we developed a computational abstraction that emulates the ability of our physical geometry of the rotation arm around two axes. And here we can see the different families that we have and how we translated it into the computational world.
So we developed this computational abstraction through simple embedded autonomous intelligence, such as number of possible array of passives without active unit, a reference and sticking to the ground, absence of ground or structural stability and self-intersecting, etc. This simple walker is referring to the ground and makes simple movements. And also we developed simple goals like finding another creature, reaching or avoiding the area. The body autonomously adjusts and optimizes its own movement sequence. When multiple bodies connect, their possibilities of actions get drastically more complex. Once they combine, they can continue their individual movement pattern in an unchanged fashion, or recalculating their movement as a sequence of combination. Here you can see a combination of climber and simple rotator.
Is to get into place or connect. And as each creature creates its own specific grid that it walks and operates on, or has a limited array of mobility and turning circle, based on the sequence of its movement, the structure creature creates and the space it can deploy of multiple ones performing on the same grid differs very much from each different simple body plan or build. So they all have their individual grids and their individual ways of aggregating together. This results in a wide array of different structures with very different qualities of growth, different qualities of how they can branch and where they can branch based on their different base unit and their different base sequence of movement and walking, and how they actually physically can get together, can get to connect. So, for example, certain body plans like the simple walker that we've seen before, which is a pretty linear sequence, can only create structures with high porosity due to their, first of all, the limited turning circle, but also to their little volumetric qualities, but strand-like body, and therefore degradation also result in porous, more scaffolding-like systems such as this. Yeah, this with around 400 units of simple walkers, and examples in the middle would be about a wall-sized structure. 1/3 of the units in this case would need to build are active units allowing the movement of its simple parts or its single units, and in this case there are only 3 possibilities of connecting, 3 active units, only 3 possibilities of connecting and branching, which results in this porous structure. And another, and for example on the top left corner you see the same amount of units in a densely packed volume, so the closest volume before extension. And overview or possible scenarios of high aggregation structures.
Shift around by connected actives on the ground plane, or if anyone decides for a potential build inside for a settlement, it starts with vertical. This goal-oriented simulations create negotiated space and dialogue between bottom-up decision-making of every single unit to act as, but can also react on outside influences and demands, encouraging both interaction and the communication.
Here are the chronology of our models. Those ones are the first explorations we did with the foldable geometries and packing logics. And here, transformational units. We also explored different packing logics here with this and the connection phases and phases that can or cannot connect. Here was the exploration of the soft faces and how these faces can inflate or deflate. This one is the unit that walks in the grid. We also kind of explored the gravitation, gravity and heaviness between one face to the other and this relation of the inflated faces. Here we can see the first walker. We tried, we activated the joints. And by these 2 activations, this unit can move back and forth in the grid. Here are the other mechanism explorations. This is a linear activation. We don't have the mechanism here anymore, but it's activated by opposing faces connections. Yeah, here as well. And here is the soft faces activation. This one is the last model we explored. This the full body walker with 3 activation units. These units are activated by this linear actuator, and by shifting the actuator a bit, it can close to one side or the other. Here are our taxonomy of different aggregation units. And those ones are the higher population explorations and single unit joints. And that's it. Thank you.
But it would be nice for you to it seems, bracket off the question of scale and really define. I mean, the irony of making a system that can assemble itself is the last thing you need to do is to make it the size of the mason who used to put the bricks down on the course of bricklayed bricks. Like, having taken that figure out of the logic of the material of the system, I think it's incredibly interesting to speculate on it being, powers of 10 larger or smaller than that first kind of rendering. And it might just be an initial intention just to have a kind of working hypothesis, but one of the implications is because of the nature of the physics involved that this being seen as, you know, a 100-to-1 model rather than a 1-to-100 would change dramatically the possibility of what you call crowd behaviors or structural performance or even space making. I think that's one of the really interesting qualities to it.
The moment we basically see them as one-to-one models, meaning as small as we can mechanically and physically scale our prototype, that is also our proposal. So the scale sizes are really by the mechanical restraints, but also by the try to scale it down, not necessarily.
I want to when you say it's non-finite, it's mobile, it's self-assembling, and you make your own kind of manifesto of what. I think that personally I see that, yeah, the non-finite is there and very much so the mobile, but the self-assembling part is not clear. In the sense that, and that's, you could go back to your question about size and whether or not the hand is still a kind of reference scale to have into account, because it's not clear how it builds itself, how the units would travel on all the units in order to...
But it would be nice for you to it seems, bracket off the question of scale and really define. I mean, the irony of making a system that can assemble itself is the last thing you need to do is to make it the size of a mason who used to put the bricks down on the course of other bricks. Like, having taken that figure out of the logic of the material of the system, I think it's incredibly interesting to speculate on it being, you know, powers of 10 larger or smaller than that first kind of rendering. And it might just be an initial intention just to have a kind of working hypothesis, but one of the implications is because of the nature of the physics involved that this being seen as, you know, a 100-to-1 model rather than a 1-to-100 would change dramatically the possibility of what you call crowd behaviors or structural performance or even space making. I think that's one of the really interesting qualities to it.
The moment we basically see them as one-to-one models, meaning as small as we can mechanically and physically scale our prototype, that is also our proposal. So the scale sizes are really by the mechanical restraints, but also by the try to scale it down, not necessarily.
I want to erect higher structures. Yeah, it seems to me that all the work that you have at the moment has to do with the transforming properties of structures, and very much, and still with that I think there is a limit to, in higher populations, to how much things can transform. And I think you're not exploring where that limit is. So on that part I think there is a problem. But the question of self-assembly is for me fundamental to not leave out of the table, because otherwise the whole project breaks down without it. And then yes, it needs to be at the scale of the hand, because eventually you're going to have to think about somebody putting this together. So
I think the issue of scale is super critical and at the same time not in the conversation. This last slide for me is the only one where you're saying that it's a return to the brick. And at the moment that was an early intuition, but we leave it as the final suggestion. Because I think these things are relational. I don't think that, I mean, like to go to Brett's point, which I think is a really important one for you guys to think about. This could be like at the scale of smart dust, or like literally like marbles, really talking about higher order operations that could be managed in principle because they are recursive geometries that you can actually really understand. So it's not an amorphous thing, it's actually a very almost like crystalline strategy of an assembly strategy. Or they can be much bigger, because I think as soon as you make it into a toy, which maybe where we started from, it's definitely not where we're in, because this image is basically suggesting that people could do the same trick.
Where is this going to be applied? You know, I would say I would emphasize a small scale for the brick, but what kind of scale are you actually going to design for? Like not the scale of the brick, but I mean, what's the scale of the space? What's the kind of activities? What's the context that this is situated in? I mean, and what can it do? Like, I mean, this slide with all the icons starts to kind of compare it to a regular building. I mean, that's an interesting start, but I think you can even go much beyond that. Like, those things are kind of, each one of these is a very pragmatic issue associated with a regular building. If you start to think of architecture as something dynamic and reconfigurable, then there's probably a whole other set of questions that we can ask about that.
Of how you got to where you are. You know, in a way that's sort of, it's on the table and in front of us, but you're still not imagining what you might want to accomplish in the relatively limited search space of the next 6 months and before you're working X number of hours a day, what you want to try and demonstrate in January. But I think it's yours to claim, definitely. It would be quite unlike.
Well, because the taxonomy, this whole, very complicated search, I really, really hate it actually. Because it fundamentally actually undoes, I think, what really is at the heart of what you're trying to do. Because I think this building up of creatures is also building up of intelligence. As soon as these things start to create these body plans, they have particular behaviors. That aspect of the behavior is not something that you're talking about. I would strip away.
What I like about it too is that then these molecules most probably, they're obviously assembled in the sense that they're temporary agglomerations of 5, or I don't know what you call them, it's quite open. It's not that you have to fix them. They stay together for a while, and they have as a group of 5, they now have a new capacity, and then they can break up into a group of 2 and a group of 3, or they become a group of 7 or something, and then it becomes something else. And the 5 are also different. And then once they have agglomerated, they, to some extent, they lose that the molecule bleeds back into something more homogeneous. So Flavia ties up a lot with the assemblage concept versus organism concept in terms of using let's say, in the social group of 50, the way they break up into groups of 2, 3, into 15, and so on. So that's what I find, and somehow, I was wondering first, is the problem you create these kind of kinetic sculptures out of these. And they initially work on the fact of surprising us and charming us in terms of the kind of versatility and surprising of kind of breaking out of these branches, arms, compacting, all that has as such not yet much purpose, and I have to kind of accept that, and maybe that's, and then you focus on that. I mean, you can try, but I mean, I haven't come up with a nobody so
exploration. So that, just so I qualify what I'm saying in the context of what's being said, I think your approach to playing in terms of prototyping, demonstrating the novelty of the kinetics and all that stuff is obviously where the project is at. I think you could use play in a serious form to actually start to really discover. I think if you assume that it's at a scale
beyond where it is, I mean, if I think about what you were implying with a lot of these things, I want to imagine what a large agglomeration does when it moves, and how that would be radically different than most buildings. In the same way, Bart is saying that it could be like gills. But imagine if a fish had gills all over its body and could open up all of a sudden like this.